Good afternoon everyone and welcome to start with a brief introduction of differential amplifier. So far we have covered the basic common source amplifier with active load. We have gone through the analysis, DC analysis, swing analysis, frequency response and also noise analysis. Now we are going to proceed towards differential amplifier, which is going to be the first stage of our op amp or two stage op amp, which is going to be employed in building the low noise front end amplifier for our analog front end. So, let us start our discussion on differential amplifiers. Now, for differential operation, the common topology that is used, you have a bias current ID, which is used to supply current to two differential pairs M1 and M2, and you have load resistances. Now, this load can be active load, just like what we have studied earlier. It can be passive load, it can be PMOS. Now, all of us are aware of what are the basic advantages of differential operation, right. So, differential operation ideally is able to reject any common mode disturbance on both the inputs. So, if you are having an input signal in a differential mode, that is the small signal applied on the top of the DC voltage Vg is having opposite polarity. So, this is minus Vg by 2 and on this one again DC voltage Vg and plus Vg by 2. So, here these two differential signals are going to produce corresponding differential signal as the output. Any common mode signal that comes in, suppose you are having at a particular time instance some disturbance, there is a kink on both sides. So, ideally a differential circuit should be able to reject this kind of common mode disturbance on the input signal. That is the advantage of a differential circuit. So, especially when we are going towards SOC, we are trying to integrate analog and digital together. Apart from the external noise sources, there are many other on chip noise sources that can come into picture, like along with the digital circuit you can have some clock signal going in nearby and it can create some common mode noise. The VDD can have some noise. So, all those appear as common mode noise, and a fully differential circuit operation can reject that common mode noise. The main operation of the differential amplifier is the output should be A times V1 minus V2 or V plus minus V minus, let me call it V out should be A times V1 minus V2, where if you are having common disturbance on both of them delta V which is a common noise Vn that should get cancelled. That is the ideal operation of a common of a differential amplifier, cancelling out any common mode disturbance. Now, here if we talk about the differential operation, like what is the operation of this amplifier if we consider the differential signal, we are applying a differential signal, what happens to the output signal and what happens to the node over here. Why are we using current source? That can be a question to start with. Can we do it without the current source also? So, there if I try to answer this, if I am directly connecting two common source amplifier ground and then you are having the input signal may be differential and on the top of that you have some common mode disturbance coming at some point. So, this kink is a common mode disturbance coming at some point. Can this circuit still give us, can this circuit still reject the common mode signal over here? So, once again if I see, if we do not have this current source, this common signal over here, that is definitely going to increase the current in both these branches, and as a result the output is going to this is going to translate to both the outputs equally as long as the circuits are well matched. So, if I talk about the single ended operation, if I am looking at the single ended output, we are not able to reject the common mode signal, whereas if I am talking about a current source, suppose I have an ideal current source tied at this node, under that condition, if I am having a common mode input, that means both the inputs are changing together, assuming that these transistors are remaining in saturation, the currents will divide equally, because VGS is same, both the inputs are changing by the same amount, therefore, the two currents are going to be same, and therefore, depending upon what load do we have over here, the two voltages over here are going to remain more or less constant, because these currents are constant as long as this transistor is in saturation and this current is constant. So, these loads are going to, these voltages are going to be constant. Suppose you have a resistive load, the ID will be dividing equally between ID by 2 from the two sides, and therefore, the output voltage over here is just VDD minus ID by 2 times RD. So, ideally it will reject any common mode signal, it will not have any fluctuation because of a common mode signal. So, that is the main advantage of having a differential operation. So, now how do we look at the common mode and differential operation of such a circuit? So, here once again we have already seen how to implement this ID, and therefore, we are just going to replace it with our actual current source little later. Before that, let us do some analysis and try to find out the behavior of this common source terminal. So, irrespective of the load connected here, if I assume that both the transistors are in saturation and I have a good current source close to ideal, and I am applying a differential signal, say plus Vg by 2 here, minus Vg by 2 here. Just looking at the small signal, I am forgetting about the DC, I am just looking about the small signal, plus Vg by 2 here, minus Vg by 2 here. So, what happens to this Vs? What can we say about the small signal at the source? I am just trying to talk about the small change in Vs that may appear because of the small differential signal applied at the two gates of M1 and M2. So, if I ignore the channel length modulation of M1 and M2, effectively I am trying to change the VGS of M1, I am also trying to change the VGS of M2, and we know that when you try to change the VGS, we are going to get a small signal current flowing from drain to source of M1, which is equal to GM1 VGS1. So, if I to say the small signal current over here is ID1 and the small signal current over here is ID2. What is ID1? If I ignore channel length modulation, ID1 can be written as GM1 times VGS1, and ID2 likewise can be written as GM2 times VGS2. Now, the third current over here, that is ID, this is ideal current source, ideally it should remain constant, it should not change. Therefore, the small signal currents ID1 and ID2 should add to 0 under all conditions. ID1 plus ID2 should add to 0, because these are just the small changes in the current capital ID1 and capital ID2, and therefore, I can write down GM1, what is VGS1, Vg by 2 minus Vs plus GM2, once again what is Vg2. So, that is we have assumed differential signal, so that becomes minus Vg2 minus Vg by 2 minus Vs Vgs2, that should be equal to 0. If you see, the first term gets cancelled, minus GM2 Vg GM1 Vg provided GM1 is equal to GM2. So, if this condition is met, the first two terms get cancelled and I am just left with GM1 Vs minus GM2 Vs equal to 0, which implies that Vs must be equal to 0. What does that mean? That Vs is not having any small signal, therefore, we can say that this is now an AC ground. So, basically the joint source terminal of these two pairs M1 and M2 is acting like an AC ground as long as we are having GM1 and GM2 matched. So, once again we need good matching between these two NMOS pairs for a good differential amplifier, so that we can have a reliable AC ground established at this point. And what if your signal is not fully differential, rather than Vg plus Vg by 2 minus Vg by 2, we can have this as a constant terminal and you can have an input which is coming over here. So, in that case we can decompose the input into V common mode and V differential. So, we can always write down the differential voltage as V 1 minus V 2 by 2 and the differential voltage as plus minus V 1 minus V 2 by 2 and the V common mode as V 1 plus V 2 by 2. And we have to see the behavior of the circuit for the common mode voltage separately and the differential voltage separately. So, I can apply plus VD1 minus VD1, that becomes a differential operation, and then I can treat the circuit for the differential mode, find out what is the output signal for the differential, and second I can also look at the behavior of the circuit to the common mode signal. Ultimately, if I add these two, it is just the input signal V1 and V2. So, I am just breaking down any arbitrary signal V1 and V2 applied at the gate, provided they are small signal, DC voltages are quite close, so that GM does not change. Important point is that the GM should be almost very similar. So, that will happen if you have the DC points same. So, provided these V1 and V2 are small signals, I can decompose them into the differential signal and the common mode signal. And then analyze the effect of this differential signal and the common mode signal separately and then add them up, because if you are talking about small signal model, it is a linear model, right. So, superposition will hold true, linear superposition will hold true. So, we can just analyze the effect of this differential signal separately, find out the output signal resulting from the differential signal, likewise find out the output signal resulting from the common mode signal, add them two together, and that gives me the overall response of the circuit on the signals V1 and V2 applied at the input terminal. So, that is how we can analyze any arbitrary signal at the input. So, for the differential case, one thing we have already figured out, if I am looking at the differential operation plus Vd by 2 minus Vd by 2, one thing we have already seen that the Vs is AC ground. We can, for the differential mode, we can always treat Vs as the AC ground. In that case, I can talk about the differential half circuit, right. For differential half circuit, I can treat the source terminal at AC ground, and then my amplifier for a given Vg by 2 is just a common source amplifier, same as before what we have done. And the entire analysis, whether we talk about the DC analysis, small signal analysis, frequency response remains same. Something is going to differ, and that is our swing analysis, and we also need to address what is going to happen to our noise analysis. Is the noise analysis going to remain same, or we need to have any difference? So, from the point of view of DC, once again we know that there is a bias current coming over here, you have some DC gate voltage over here, and the minimum drain voltage that you can have is going to be, suppose there is a DC voltage capital Vg, there is a DC bias point for both the sides, and the minimum output voltage you can have is again going to be Vg minus Vt, but this Vg is also going to be determined by some other constraint, and that is given by the constraint produced by the current source. So, for AC analysis, the common source point is AC ground, Vs equal to 0, but from the point of view of DC, I need to look at the capital Vg which can accommodate enough drain to sources voltage for the current source. So, if I talk about the AC analysis and try to go back and place my current source over here, the one we have already used in our common source amplifier. So, you have some I ref, you are having diode connected transistor, and then you are trying to mirror this. So, this is the current source, non ideal current source. You have of course have some finite output resistance, but close to an good current source is what we have now. And we know that corresponding to this I ref, how to calculate the Vgn, equate the equation for current in say call it M1, M2, M3 and M4. We can equate the equation of current in MOSFET and find out the Vgn required to support the I ref, and therefore, under that condition we know what is the minimum drain voltage that M3 can have. So, I can say Vd3 min is going to be Vgn minus Vt, I call it Vt3. Now, I know that if these are having the same ratio, I have I ref by 2 flowing through each of these for the DC biasing point. For DC biasing point, each gate voltage is capital VG, and I have IRF by 2, IRF by 2 flowing through both of them, and therefore, once again I can find out the required VG S3, which is going to be a function of I ref by 2, because we know I ref by 2 is once again VG S3 minus VT 3 square times the Kn. So, I can obtain VG S3 as well as VG S2, both of them are equal as long as the two devices are well matched. And then for a given minimum VD3, we can say what is going to be the minimum gate voltage that you can have over here. So, that becomes VG3 min, that is equal to VD3 min plus VG S3. And then for this particular DC voltage at the gate, we can find out what is the VD1 min or VD2 min, which is going to be VG3 min minus VT3. So, this gives us the limit on the minimum voltage or the drain voltage that I can have for M1 and M2. For a resistive load, the maximum voltage that I can have at M1 and M2 drain is just VDD. So, VD1 max equal to VD2 max is just equal to VDD. So, the upper point does not change, VD1 max and VD2 max do not change, but VD1 min and VD2 min, they are again slightly higher, because you need to have enough VDS for M3. The VD, this node is not a DC ground, this is an AC ground. From the point of view of DC, you do need some minimum drain voltage for M3 to keep M3 in saturation and make it behave like a good current source. So, that is the difference which comes with respect to the signal swing. Now, in case of differential analysis, we have already seen that this is a differential half circuit. So, if I am applying a fully differential signal, that is plus Vg by 2 on one gate and minus Vg by 2 another gate, this is the AC ground, and therefore, the gain is going to be just Vg by 2 times GMRD. Likewise, on the other side, Vg by 2 times GMRD, and you take the difference. So, VO1 is Vg by 2 times GMRD with a minus sign, and VO2 likewise plus Vg by 2 minus Vg by 2 times minus GMRD. So, plus you are getting another plus sign, and therefore, the output signal, which is VO1 minus VO2, will be just Vg times GMRD. So, this is the gain, we are just getting GMRD as the small signal gain, VO1 minus VO2 divided by V in 1 minus V in 2. So, the small signal analysis for the differential operation remains same. What about the small signal analysis for the common mode case? So, for the common mode case, how do we deal with it? So, if I have to draw the circuit for the common mode operation, what we are talking about is applying the same DC or same AC signal at the two gates. So, basically we are going to pull these two gate voltages up and down by same amount, that is the common mode. So, under that condition, we can say the source voltages are anyway common, the two transistors are very well matched, the gate voltages are also common, we are having the same gate voltages. So, basically we are tying up the two gates together. As long as the two MOSFETs are matched and the two RDs are matched, we expect that the drain voltages are also going to be same, they are going to change by similar fashion. Therefore, we can tie them also together, and we can then arrive at the equivalent common mode half circuit by tying these two branches together, because gate voltage is same, the source voltage is same, and the drain voltage is same. But in this case, definitely we do not expect that this node is going to be AC ground, right, because again if I assume that this is behaving like a good current source, this is providing an ideal current, DC current, these two VGS will remain almost same, they will remain almost constant. So, if I am pulling the VG up, in order to keep the same VGS, the source will also go up and down, up and down. So, source is no longer AC ground for common mode operation. If you are trying to pull up the gate voltages, the source voltage will also be pulled up by same amount, so that the VGS of these two transistors remain same, and so that they keep supporting the same current I ref by 2. So, source is no longer AC ground. So, in the common mode half circuit I need to consider the transistor M3 also. I cannot just ignore it, I cannot put an AC ground over here. Now, if I talk about M3, what is the role of M3? How do I model M3's behavior on this circuit? Once again, as long as M3 is in saturation, this is a NMOS transistor with gate voltage constant. Looking into the drain, I have an equivalent small signal resistance provided by M3, and that is just equal to RO3. So, again, for small signal analysis, I can replace M3 by its equivalent small signal resistance RO3. So, I can replace M3 by RO3. I am tying the two transistors M1 and M2 together. So, this becomes 2 times W by L of individual M1 and M2. I am also tying the two RDs together. So, this becomes RD by 2, and therefore, this is my common mode half circuit, right. So, I just tied the two transistors together. So, of course, if I talk about the GM, now this is 2 times W by L, I have tied both the transistors together, and the ID in this combined transistor is equal to I ref. Initially the two transistors were having I ref by 2, I ref by 2, now this combined transistor of length 2 times W by L is having a total current of I ref. So, we have W by L 2, I ref twice, and therefore, we are having GM which is 2 times GM of the individual transistors. So, now I can do the small signal analysis, that if you are applying a common mode VCM, the small signal VCM at the gate, what is the output voltage V out, small signal output voltage resulting from this. Now, this is something like a common source amplifier with source degeneration resistance. Many of you might have seen it, those who are into analog courses, teaching and research, we are very familiar with this topology, common source amplifier with a source degeneration resistance. We just want to quickly derive it. How are we going to do this? You are now in a normal common source amplifier, we have the source connected to AC ground, but now we do not have this at ground, we have an RO3 over here. So, I can quickly drive the small signal model. We have VCM applied at the gate, this is the gate terminal. We are having GM VGS as the current source between the drain and the source. Between the drain and the VDD, I have RD by 2, so I can call it RD by 2. I am ignoring RO by 2 for the time being for simplicity as compared to RD by 2, and then my analysis is relatively simple. I have RO3 between the source and the AC ground. Remember, RD is between the drain and VDD. For small signal, VDD is also AC ground. So, RD by 2 appears between drain and the AC ground, RO3 appears between the source and the AC ground. Now, we have this small signal equivalent circuit for this case, and I can try to solve it and find out what is the relationship of VD as compared to VCM. So, what we can say is, I can write the KCL over here, I can say GM VGS is the current coming here, which is just equal to Vs, which is the node voltage over here, upon RO3. Whatever current comes, the same current goes. Vs upon RO3 is the current flowing through RO3, which is equal to GM VGS, where Vg is VCM, Vs is the source voltage upon RO3, and therefore, I can find out the expression for Vs, Gm plus 1 upon RO3, that is equal to VCM times Gm. Therefore, Vs is VCM times Gm upon Gm plus 1 upon RO3, and therefore, VGS is going to be VCM minus Vs, right. So, I can write down VGS as VCM minus this quantity. So, I have 1 minus this quantity. So, Gm gets out and we have RO3 upon Gm plus 1 upon RO3, and then I can say what is going to happen to the small signal Vd over here. So, whatever current is flowing from Vs to the ground through RO3, same current must exit through RD by 2. So, we do not have any other path. So, Vs upon RO3, I can say Vs upon RO3 must be equal to minus the current flow over here, which is minus Vd upon Rd by 2. Therefore, this is just going to be Vd is just going to be equal to Vs upon Ro3 times Rd by 2 with a minus sign. So, I can write this down as Vcm times Gm Rd by 2 upon 1 plus Gm Ro3. So, basically Gm Rd upon 1 plus Gm Rs, this is the Rs, the source resistance in this case, this is what we are getting. So, this is the original gain for the differential amplifier when this would have been source, this would have been ground, then we would get Gm Rd by 2, but in the denominator now we have 1 plus Gm Ro3, which can be a large number. Gm Ro3 is the intrinsic gain of the MOSFET, can be much larger than 1. So, in fact, this can be approximated as you can ignore this 1 in comparison with Gm Ro3, and therefore, we can cancel the Gm and we are left with Rd bound to Ro3. So, this is the magnitude of the common mode gain that we are getting from the input to the output, and it tells us that if your Ro3 is large, we are going to get very small common mode gain. The common mode voltage over here, the output voltage over here is not going to have any significant swing. So, having a larger Ro3, that means having a larger output impedance for the current mirror is going to be advantageous, that is going to give us a larger small signal resistance, and that is going to give us smaller common mode gain that is ideally required for a good differential amplifier. So, one of the very important parameters that is required for the differential amplifier is common mode rejection ratio, that is defined as the differential gain versus the common mode gain. So, how well the amplifier is amplifying the differential signal and how well it is rejecting the common mode signal. So, we have seen in this case the differential gain is Gm Rd, common mode gain is Rd upon 2 Ro3. Therefore, the common mode rejection ratio, if I have to say CMRR, which is A differential upon A common mode magnitude, that is just Gm Rd upon 2 Ro3. So, basically Gm times Ro3. So, larger Ro3 is going to give us conducive to good common mode rejection ratio. It is going to give us a better differential amplifier operation, and we have seen how to make the Ro3 large. One of the possibility is to increase the channel length of M3, so that we can have larger common mode rejection ratio, larger Ro3, because remember Ro3 is 1 upon lambda Id, and if you increase the L, lambda reduces. So, larger channel length of M3 can be conducive to a better CMRR. But what is the disadvantage if I try to make the M3 channel length larger, the VGS required will be larger for a given current. But once again I can make the W of M3 large, because from the point of view of AC, it may not it may not give you a problem as far as the differential signal is concerned. But once again, if I talk about common mode response, if this is the common mode half circuit and if I am trying to make M3 very large, what happens? You are having some parasitic capacitance between this node and ground, which is resulting from several transistors M1, M2 as well as M3. If I make M3 very large, once again this parasitic capacitance will go on increasing, and at higher frequencies the impedance, combined impedance of this parasitic capacitance and Ro3 will drop. As a result, the common mode rejection ratio will drop. So, there are the trade offs. So, you can try to increase the W by L of the bottom current source transistor, you can try to make the channel length large, you can try to reduce the overhead voltage headroom required by M3. Then once again, if you are having larger size for this M3, it increases the overall parasitic capacitance at this node, and thus in turn can degrade the common mode rejection ratio at higher frequency, because it is going to reduce the impedance, effective impedance between this node and ground. So, there are always trade offs associated with differential amplifier design. Now, so this is regarding the differential operation and common mode operation, the small signal analysis, differential gain and common mode gain for the simple differential amplifier with resistive load. We have also seen the swing, we have seen the DC analysis and the small signal analysis. Frequency analysis, for the common mode we briefly discussed what is going to happen if you make the M3 large in order to have a larger L, or in order to have a smaller headroom that is going to increase this parasitic capacitance, and again it is going to reduce your common mode rejection ratio. That is an undesirable thing. Regarding differential case, the circuit is same as what we have analyzed in the common source example. So, we do not need to talk a lot about the differential case. Frequency response is going to be more or less similar as what we discussed in the common source case. In case you are having a source resistance over here, the same thing, you can apply the Miller effect, break down the capacitances. So, exactly the same expression that we obtained for the common source. No need to discuss it further for the time being. What about the noise? So, do we need to do something else with the noise? So, we are talking about the differential operation. What happens to the differential operation if we are talking about the common mode, the noise produced by these transistors? So, differential operation we are considering M1. So, definitely the effect of noise on M1 is going to be similar, we are going to do similar analysis. M2 also similar. Only thing that we have to take into account is that noises or noise voltage, we do not consider their polarities, we are going to consider their mean square value. So, though we cannot say that the values over here will be Vn1 minus Vn2, it is just the mean square value. So, we need to look at the mean square noise at this point using the half circuit, which is going to be same as what we did for common source. What about M3? M3, if I talk about the noise of M3, it is definitely having an input referred noise over here. I can convert the channel current noise into input noise voltage, and therefore, I assume that it may have some effect at the output, because here you have a noise voltage Vng square, Vng3 square, and that may affect the two outputs over here. So, what is that effect? So, are we concerned about the noise of M3 in this case on the output? So, if we talk about M1 and M2, they are independent transistors, their noises are not correlated. Therefore, we cannot cancel them out because of differential operation. We have to look at Vn1 square and Vn2 square produced by M1 and M2 in the separate half circuits. But M3, if we are talking about the effect of this noise on the two branches over here, this is common source, this is a common noise source. So, the effect of this common noise source on these two are correlated, it is not independent source. Therefore, we can say that we can cancel out, we will not really require to consider the effect of the equivalent noise voltage of M3 on the two outputs, because it is going to have this is the same noise source producing the output voltages at this point, and therefore, we can ignore the effect of this equivalent input referred noise of M3 and just be concerned about the noise of M1 and M2 to the first order. So, this is regarding the DC small signal swing and the noise analysis of differential amplifier with resistive load. Now, in case of our designs that we are looking at, we are going to use active load differential amplifier with active load, and we have already had the discussions on the common source amplifier with active load, how to do the analysis like the DC, AC, small signal and noise. So, now if I replace this RD by PMOS load, once again the entire analysis for the differential half circuit remains same, common mode half circuit once again remains similar to what we have done for the resistive case. Only thing is, rather than RD you have a RO coming over there. So, let us briefly discuss the differential amplifier with active load. We are going to deal with two kinds of load for the differential amplifier. One is going to be current source load and another one is going to be current mirror load, which are both going to be utilized in our front end amplifier. So, I am not drawing the reference branch, it is assumed that this is connected to a reference branch. the second one over here, this is something very similar to what we have already done, common current source load, and we are assuming that these current sources are once again coming from a reference PMOS current mirror. You do not have any connection over here, it is just to show that these two are just acting like current mirrors. So, here the M1, M2, M3, M4, they are M3 is forming current mirror with M5, M4 is also forming current mirror with M5. So, both of them are current mirrors with the reference branch as M5. In this case, that is not the scenario. Here you have one of the branches M3 diode connected. We are not using any reference branch, we are not using a current mirror, separate current mirror for obtaining Vg. Here, as we are seeing, output is single ended, we are taking the output only at one point. Here, the input as well as output both are differential. So, in this case, input is differential, output is single ended. In this case, input is differential, output is also differential. So, this is fully differential amplifier, and definitely it is going to have advantage whenever we are having several stages, multiple stages, and you want to keep the signal differential all throughout. We will prefer fully differential operation. We do not want to convert it into single ended signal at any point, unless we have processed the signal sufficiently, we have amplified it sufficiently. Now, it is ready for digitization. Even for digitization, people now prefer fully differential amplifiers, comparators, which can have better robustness. So, in today's mixed signal design, we can have the entire chain up to the ADC amplifier and the comparators being completely differential, fully differential. So, we are going to use this fully differential amplifier as the main amplifier in our design. This is going to be the first stage of our front end amplifier, but we are going to need assistance from another current mirror load amplifier with a single ended. We will see why. Now, if I talk about the current source load, here once again if I draw the same analogy, you are having the differential signal Vg by 2 plus minus. This node becomes an AC ground. This is the DC bias provided by the reference branch. This again becomes an AC ground. Therefore, the half circuit of this is very similar to what we have already done today. This is an AC ground, the input signal is applied here plus Vg by 2, and this is an AC ground. This is M1 and this is M3. So, this is the half circuit, and therefore, the DC analysis, small signal analysis, frequency response, noise analysis, everything remains same. Only thing we have to remember is the signal swing is going to have another factor of VDS, call it M5, VDS5, because depending upon the VG5, we need a minimum voltage here, VD 5 min is equal to VG5 minus VT, and then on the top of that we have this transistor. So, that is the only difference we have just discussed in case of the resistive load also. So, we are having some voltage headroom consumed by M5. We say this M5 current source is consuming some minimum voltage headroom, and apart from that, rest of the things, rest of the analysis for the differential circuit remains same as what we have done. The considerations regarding the bandwidth, the noise and the small signal gain all remain same. So, we do not have to discuss much about these 4 analyses. However, we have to discuss something about the biasing. How do we bias the DC nodes, the drain nodes? So, while discussing the single ended common source amplifier with active load, we discussed a problem that Vd is very ill defined. We do not have a very good control of Vd. So, if we recall our derivation of the Vd, we saw that the Vd is going to be strongly dependent upon the lambda, and therefore, it is not a very well defined quantity. But in differential circuits, we do have some mechanisms through which we can try to stabilize the Vd. So, we will see that how to with the help of the second amplifier over here, which is the amplifier with current mirror load, we can obtain a desired DC point at the output of this first amplifier. What about the second one? It is going to help the first one but before that it has to help itself. Does it have a well defined DC point? If the answer is yes, then this guy can help the second one, but if this itself it does not have a well defined DC point at the output, then we can remember the announcement made by the air hostesses. It should wear its mask first. First of all, it should help itself. So, let us see whether this can help itself. So, how do we define the DC point at the output of this stage? So, we are having a different kind of load, one of them is diode connected, and if we assume that this M5 is acting like a good current source, where ID5 is relatively constant, M5 is remaining in saturation. For common mode, as long as these two signals are close together, gate voltages are close together, suppose AC signal is 0, both the gate voltages are having same DC point, IREF is going to divide equally between these two nodes. Therefore, in this branch I have IREF by 2, and this is something similar to our reference branch of the current mirror. So, this can produce a reference gate voltage VG3 using the quadratic dependency. So, this VG3 is not strongly dependent upon lambda, it is having quadratic dependency. I can solve IREF by 2 is equal to 1 upon 2 mu p CO x W by L VSG, which is VDD minus VD3 square 1 plus lambda p VSD, which is once again VDD minus VG3, and assuming VG3 is going to be few tens or hundreds of millivolt below VDD or below again another term VTP, mod VTP, missed it. So, again the lambda dependency is much weaker, because here you have a much stronger dependency determined by the square term or the quadratic term. So, here the VG3 is not primarily determined by the lambda, rather it is determined by the quadratic term. So, we have a scenario similar to the diode connected branch of the reference current source, and therefore, we do have a relatively well defined VG3. Now, once this VG3 is available, it is applied to the gate of M4, and therefore, this is again acting like a current mirror. This is the reference branch of the current mirror, this is something like the output branch of the current mirror. As long as both the input voltages over here are close, if I talk about DC condition, we are having IREF by 2 in both the branches, VG is same for both of them, VSG is same for both M3 and M4, and if these two transistors are matched, we can assume that the DC voltage here is also going to be close to the DC voltage at this point. So, this current mirror action is ensuring a relatively well defined DC voltage at the output in this circuit. So, we have a relatively well defined DC point over here, which is determined by VSG of M3. Here the V out is not strongly dependent upon lambda, and remember, when it is dependent upon lambda, the problem is that lambda is very small and it requires a very large change in VD, the source to drain voltage, to accommodate for any imbalance, whereas in case of the quadratic dependence, it is a much stronger dependence on VG3. So, here VG3 is getting dictated by the quadratic dependence. I can altogether ignore this value. So, if I talk about say some values, practical values for 180 nanometer, this is 1.8, VTP close to say 0.3. So, you are having 0.3, and VG3 will be close to VDD. So, that you have an overdrive voltage of around say 0.2, 0.3 volts. So, it is something like 1.2 or 1.3, something like that. So, you have a few hundreds of millivolt overdrive. This is the overdrive voltage VSG minus VTP. We are talking about something like 0.3, 0.4 volts, maybe lower than that. If your current is smaller, maybe 0.1 volt and lower. But this quantity can be say 0.01, and once again this is 1.8 minus VG3 around 1.2. So, as compared to the first term, the second term is very small, 1.8 minus 1.2 times 0.01, because this lambda factor, the dependency on the second term is much smaller, and therefore, VG3 is going to be determined mainly by, or the VG3 is mainly determined by the quadratic term and not so much by the the lambda term. In earlier case, in this particular case, the Vg3 is fixed. We are fixing the Vg3, forcing the Vg3 equal to the Vg of M5. So, there we do not have any chance of adjusting Vg3, it is fixed or dictated by the Vg of M5, but in this case the Vg3 is being set by the Iref by 2, it is not dictated by another branch. So, it is setting the Vg3 by the dependence on threshold voltage of M3 and W by L of M3. So, basically the W by L of M3 and threshold voltage of M3 is going to determine what is my Vg3. And as a result, for common mode operation, I am looking at only the DC conditions, these two branches being very well matched, the V out over here, the DC condition is going to be equal to Vg3. So, we have a very well defined DC point, and this can be used to help our first amplifier, which has a ill defined DC point. So, thanks a lot, we will see you tomorrow. Good night all of you.